I want to thank the organizer of the conference for inviting me to come and tell you my opinions on the tragic events you faced. And it's indeed a particular pleasure to come to Japan because I'm a small person and have always been a bit shorter than my friends and families, so it's nice to come to a place where more people are the right height than they are in America. So that having been said, that's in any situation, I've been arguing for the last 35, 40 years, you compare the risk and the benefit. And if you don't know the risk or the benefit, you have to make an estimate and maybe study to find out. But you can't ignore it just because you don't know. You shouldn't ignore it. The comparison is done all the time, sometimes explicit, sometimes implicit. And so the question now comes, if the situation changes, such as in an unexpected accident, you should immediately change the risk-benefit calculation. It's appropriate. And that is what has not been done. It's true for any technology, whether it's nuclear or anything else. So it's best to have the calculation done in advance so that panic doesn't set in. So what's the effects of radiation on people? And what do we know from the previous instance? And it's said that those who don't understand history are condemned to repeat it. And that's happening. Medical x-rays. It's been known, used for ages. Radium dial painters. Hiroshima and Nagasaki. Wind scale reaction in the UK. 3 Mile Island. Chernobyl. The Tokai incident and the criticality incident in Japan, and the theft of a medical source in Brazil. We'll come back to that. So now, what about the medical x-rays? The advantage of medical x-rays is great. One can see a fracture for the first time, and that was fantastic. So physicians argued correctly in 1900 the medical x-rays were so beneficial that they outweighed any adverse effect. But the same benefit could have been gained with 100 times less risk. And it took crazy physicists like me. As late as 1980, X-rays were done badly in the United States. I'm one person who measured my X-ray dose when I had my X-rays done and had to be done, and they were 100 times higher than they needed them. So let's see, nuclear power in ordinary operation has a similar effect. Radiation doses can be kept very small, both for the public and for the workers, so easily and for a cost much less than the cost of the power plant and the cost of electricity. So you do it. It pays you to do it rather than to argue. Therefore, cost-benefit says to do so and make doses as low as reasonably achievable. But when something happens out of the ordinary account, this calculation is no longer correct. So the basic elements of a more appropriate calculation can be found from a combination of basic science and from history, and should be understood by at least some people, the people in authority, in advance. Firstly, what are the effects? The acute radiation syndrome or acute radiation sickness, tremendously appointment, and you must avoid them. It can happen if a dose within a week is greater than 2 sieverts. Maybe. They result in deaths within a few days. So you'd want to avoid that. What happens at 400 grams for half the people, the guts are destroyed and death soon follows. And you can improve it a little bit by having a blood transfusion, but not much. So evacuation to avoid ARS is appropriate, and an immediate evacuation if you think it might be happening. At Fukushima, no one in the public got ARS. The highest exposed worker was 0.2 sieverts. That's the worst I've come across. In fact, 0.23, I think it was. So that's far from acute radiation sickness. So no more radiation could have been allowed as soon as an accident occurred. So the immediate evacuation was unnecessary. So I would accuse that the other thing is that if you delay the evacuation, then you can think about it and make a wiser decision. Now the chronic effect, doses can accumulate over the years. The chronic effect can be related to the cumulative dose, cancer, heart disease, genetic effects, of which cancer is the only one which is important, and I'll talk about it. There are no cancers caused which are specific to radiation. What happens is that radiation causes an increase in the natural cancer rate, and that's very important. If someone gets a cancer, you don't know automatically whether it's a natural cancer or a radiation-caused cancer. Perhaps at 2 sieverts, 330% increase in cancer rate, maybe much less. Now, what did history say one should do? Well, certainly in Europe, a big effect would be the following chain. Iodine drops on the ground, cows eat the grass and concentrate iodine in milk, cow children drink milk, concentrate on the thyroid, so break this chain at once. This was known over 60 years ago. Windscale in 1957 confirmed this. Tell the children not to drink local milk for a month. And this was not done early enough at Chernobyl, and there was conflicting stories on that of people trying to protect their reputations. But the KGB stopped people and put from telling their school children not to drink milk. I saw no cows at Fukushima, so that's not the rule, and we heard about it earlier today. So what I think the immediate action to be planned in advance. Immediately something is out of the ordinary, allow the radiation exposure standards to rise at once to an earlier level. 10 rems, 0.1 sieverts average per accident. That's average over a group of people. 80 rems for life-saving activities, 0.8 sieverts. If you're an astronaut, it's 0.8 sieverts. It's already as low for average. More for elderly volunteers. If no AVRS occurs, then don't evacuate at all for 2 days to allow the carefully considered wise decision. And that may make a lot of difference. Now, this is, I apologize for the thing superimposed, that's the only picture I had of the first explosion in, I believe, Unit 3. And it blew out to sea. Very important thing to notice. First hydrogen explosion, the wind was blowing out to sea. That explosion happened because it's very important that there was a cesium, there was interactions of the cladding, zirconium, water interaction, which not only reached the first protection against the release, it also increased the heat rate by nearly a factor of 10. The wind was blowing out to sea, that was good. So I evaluate, you want to evaluate the effects of site boundary. So what did I do? My calculum was a day late, waiting for the numbers to be available in English or German. And there's the numbers in German, starting at the bottom, and the releases weren't very much until the first few days, and I was able to say, look, don't worry about very much. But then accident Wednesdays, you see the big releases, this is site boundary doses. And I just calculated, you take the peak and you multiply by the width, and I make the assumption it's all cesium, which is probably not true, noble gases. So this is my first calculation. risk probably by noble gases with little effect dose. Take the peak multiply the week. I found that boundary dose and it was falling. But I had 2 CAT scans last year and I had more dose than this. So would I be worried? Well, of course I won't be because I'm 86, and if I had developed cancer and when I'm 800, it'll be the least of my worries. So let me go back to a report I wrote after 3 Mile Island for the governor of Massachusetts, a small committee of 3 of us, unpaid. Only a few isotopes actually matter. It's important that the driving force is necessary to disperse them. That's very crucial. Stop a lot of nonsense if you remind people of that. TMI, there was almost no dispersive force for the radioactivity that's released. Chernobyl, the initial explosion was a huge dispersion. But then there was a graphite fire at 4,000 degrees Fahrenheit, and about 2,200 degrees centigrade, and that released almost a lot of stuff that's going on. Fukushima, only the hydrogen explosion and the fuel heating, no sign of graphite fire, so that's important. Now this is out of the report we had at that time, and I apologize for the report. It wasn't very good. At that time, the things I missed. And here, where was the, oh yeah. These were the temperature. This is the iodine 131, 133 of the things we talk about. Very important, you can't stop them coming out. At Chernobyl, for example, 100% of them got out. Cesium, they come later, and this is the temperature at which they will sublimate. If you don't get higher than 66, if you only get 400 degrees centigrade, then they won't come out at all. And these other ones, you can see the much higher temperature before them to sublimate, and indeed, even at Chernobyl, we got comparatively little of the telluriums and strontiums and stuff. So we learned that from history. And we also learned, of course, from we heard some of it yesterday, the last talk. So products of fission is repeated, the gases, noble gases, there we got so solids sublimate. So there was, unfortunately, the table was not broken down by age. That was a weakness of my report, and I apologize for it. Now, here's an interesting question. People talk about major accidents in man-rams. What is important to decision and what to do about it, an individual person wants to know. So, we see what's a man or see what's a person. So so the important thing in an individual is the actual effect by an individual and the group of individuals. This is all emphasized by the late Rosalind Yalow, who got the Nobel Prize in medicine. But she was emphasizing in her articles on radiation in the service of man. So traditionally, health physicists assume a linear dose response, then it's clear the societal effect is better exposed in man-REMs or person sieverts. That's its total societal response. So what about the adverse effects of evacuation? Stress can increase cancer rates 5% or more. We knew that from 3 Mile Island. Direct loss of life due to lack of facilities in addition. No one seemed to consider those at all in the decision process. Now we know, for example, they could have been discussed in advance. After 3 Mile Island, they were discussed extensively by scientists, and indeed, if there were casualties at 3 Mile Island, they were all due to the adverse effects of evacuation, which were very complicated. Now we get a statement which I'm going to have to apologize for. Seeing those big accidents, spontaneously the chairman of the U.S. Nuclear Regulatory Commission made this testament to a budget thing in Congress. Recently, the NRC made a recommendation that based on the available information we have, that for a comparable situation in the United States, we would recommend an evacuation of a much larger radius than been currently applied in Japan. So after this recommendation, Japan has issued a statement to Americans believe it's appropriate to evacuate to a larger distance, up to approximately 50 miles. That was done on the Wednesday. The Department of Energy at the same time was having a meeting, of which I happen to know who was present, and I had a report on the personal report on the meeting, and they said something different, and they were not consulted. And the next day, there was not accompanied by a justification. I formally objected with a cable to the Nuclear Regulatory Commission, who did not acknowledge my cable. JAXA's recommendation was echoed by the President Obama, had an immediate deleterious effect. It's not, to my knowledge, explained or withdrawn by either Dr. JAXA or the President. So, recommendation. So once the President had sent something, motives other than the public health took precedence. Example, sensible discussion became difficult. Media editors would no longer omit letters and comments from radiation experts. They were just turned back. I was effectively silenced from the public. Sensible journalists, whom I knew there existed a few, they were cowed. They would not comment on the effects of anything. And your Japanese media amplified it still further. So I want to say it's important to do this right. One public trust is lost. It takes much to regain. I'm committed to help you again internationally. I cannot speak for either Dr. Jackson or for Dr. President Obama, but I make a personal apology to all the Japanese people. I regret I was unable to stop those damaging statements. I've requested a formal review by the Nuclear Regulatory Commission, and there's the comment on it. They didn't like my doing that, but it's there in the public record. So what was the effect of radiation on the way to Tokyo? I looked at the things published by MEXT. I noted, of course, I first heard about them from the Department of Energy, who were not publishing, and also by KEK. First slide is from MEXT, from Ibaraki province. And you look at it, the cumulative dose was 40 milligrams, 0.45 sieverts, about 1/10 of the yearly background. Now look at the data on microsieverts per hour. Scientists always plot data so that you can see an effect. But you put it in slightly different units. It looks much less. And that may be a mistake in public presentation. This, of course, was due to KEK. My friends at KEK, I trusted that thing rather better than I ever trusted the other one. I know them. Subsequent studies, which we see those, confirm no one got acute radiation syndrome. Highest exposure is about 30 rand in a worker, not 400 rand. If there are cancers, the probability of causation, that is to say, the probability of causation is the probability of getting an increase in cancer divided by the probability of total probability, including it happening naturally. So it'll be less than 50% in all but a few cases. That's what's important. But it's important for the future understanding that people understand the argument for low-dose linearity, which I happen to believe in. When the dose is low, it shouldn't matter that much. So here is the typical problem. You have a response on the top right-hand side. You see some data, which mostly comes from various places, with a statistical error on it. What you're interested in down on the left-hand side. And you can either say it's linear, or you can say it's called a hockey stick, or you can say it's hormesis, it's good for you. But why do we say it's linear? And here we get a fundamental point. I'll go forward one. Here we are. Firstly, it's a general argument. And the general argument, if you get, since it's the same type of cancer as a natural cancer, you assume that somewhere along the process of getting the cancer, the radiation acts in the same way. So there, on the left-hand side, you see a curve which you might assume is a biological curve. And right at the point, but you get a response naturally. So at the point when that meets a dose, the natural dose, you actually get an assumed dose equivalent to what you might do with radiation. And then a slight increase of cancer over background, increased by an excess dose, and it becomes a linear dose response. So that's very important. Oh, pardon me, I'm going backwards. So then, having got that, so the cancer over background and the excess dose is then linear. It's important to realize it's general. For example, the probability of dying in a car accident in Harvard Square is roughly proportional to the number of cars. If there are no cars, you won't get a car accident. If you knew which car was going to hit you, you would stop it being made in Detroit, or even by Toshiba. So the fundamental thing, if the medical outcome is not distinguishable from an outcome that occurs naturally, then the argument applies. It's inherent in what the medical people call the multi-stage theory of cancer, which is propounded primarily by Sir Richard Doll, who died a couple of years ago. It also applies to lung effects caused by air pollution, as one of the things Doug Dockery and I have been thinking about for a long time. So this is some data. There was lots of data. This is the biological effects of ionizing radiation from the National Academy of Sciences. This is a report of a few years ago. The chairman of this report was in fact John Monson, who is from the Harvard School of Public Health. Again, it wasn't broken down by age, which is unfortunate. So now we look at that. That, of course, is we found out the big deposition was to the northwest, and what do you do about it? I looked at the numbers produced by MEXT, and the highest I found over here, and I asked myself, let's take high numbers, what do they mean? And that's the integration in red is integration for the next 12 months. That's already about what's happened. I noticed, by the way, that's outside. If we were in a brick building, it would be mostly 1/10 of that, because it does a bit of sheltering, maybe 4 times of a quarter of that if it's an ordinary building. So we must remember that. And if people have taken shelter, indeed, it's very important. Now, so what should the decision maker have done at the time of the accident? And now I'm putting, definitely, I think you should all ask yourself these questions, and I'm giving you my personal answer. Can an order an immediate evacuation? Many kilometers? No. Make it easy for any voluntary evacuation. And I would say yes, because one of the problems with Katrina we heard about earlier today was that people got confused and there was panic in the evacuation, and the evacuation routes got blocked, so they must help people in a voluntary evacuation. Do simple steps to reduce exposure to fallout, including measurement? Yes. Order all-out cleanup for years? I think no. Estimate individual things in voluntary steps? Yes. And that's all described in a paper I've just got out. And here's, compare the accident in Man-Ram's thing at the bottom and at the top, those, if you calculate, compared with other disasters. And you must recognize, disaster, bad though that was, natural background every year produces 2,000 times the number of cancers in the world as Fukushima did in a person's lifetime. Thank you. don't know.